Okay, so today what we're going to do is take a look at complex fractions. Now, a complex fraction is a fraction within a fraction. That's all it is. And these come up a lot. I'm teaching a lesson right now in physics in what's called equivalent resistance in a circuit. And resistors in parallel exhibit this property. They have reciprocal sums. And you end up using, and you have parts where there's fractions within fractions. Okay? Now, the steps are very simple. Find an LCD for all of the fractions involved. So look at all the denominators. There might be 5 fractions. Find one LCD for all of them. Okay? Then multiply both the numerator, that should be singular, not numerators, both the numerator and denominator of the major fraction by this LCD, and then simplify. It's really quite easy, but at the same time, if you don't get it, it's like, what's going on? So the issue with this topic is sometimes students get lost, and sometimes they get it right away. So if you get it right away, bear with others that might not get it right away. Is that clear? Okay, if you see it and it's easy, it's like, all right, that's good. But it's not very clear always. This is one of those things that's a weird topic. There's usually nobody in between. It's like you get it or you don't. We want to make sure that everybody gets it. Is that clear? Let's take a look at the first example and you'll see this. The first example is going to have numerical denominators. The next one will have variable denominators. So example 1. Ooh, hang on a sec. So example 1 here, we're going to see we have fractions within fractions. That's what a complex fraction is. So x over 6 is one fraction. X over 3 is another. X over 5 is another. 7 over 10 is the last. So how many denominators are there in this problem, Joe?
8, 4.
4. Now, this itself is a major denominator. This is the major numerator. But as far as the minor denominators go, there are 4 of them. Agreed? What's the common multiple of this? Least common multiple, which would give us the denominator. 30. Now, maybe you didn't know that. You didn't know it was 30, okay? So what do? Break up your denominators into their factors, just like we said yesterday. We broke it up into the factors. What does 6 factor into, Joe? Back to you, Joe. What does 6 factor into?
2,
Thank you. Julia, how about the 10?
2 and 5.
Yeah. So take a look. I didn't ask for 3 and 5. Why? Because they are, thank you, prime. So all of the primes, take a look at all the primes. 2 occurs once, right? No more than once in any of them. 3 occurs once, at least in one of them. And 5 occurs. Nothing else occurs, right? There's no doubles of any of them in any of them individually. What's 2 times 3? What's 6 times 5? There's your least common denominator. Always break up your denominators into their factors. It will work every time. Is that clear? Because in a minute, when we have variables, this becomes much more difficult. With numbers, it's easy. 30, boom, you're done. Okay? Now, once you do that, you have to follow step 2. I'm going to rewrite it. What was it again? X over 6 minus... Thank you. Is this plus or minus in the bottom? Thank you. Okay, so our least common denominator was 30. So here's what we do. Read step 2. Physically read it out loud, somebody. Who wants to read it? Ryan, go ahead.
Multiply numerator denominator by the LCD and simplify.
Yeah, so that's literally what we're doing. So we need to multiply this whole numerator by a 30 and this one by a 30. But some students get confused. So we want to multiply this entire numerator by 30 and this entire denominator by 30. But you know what? Let's multiply them by 30 over 1 and 30 over 1, which is the same thing, right? Anything over 1 is itself. The reason I'm doing this is so that you can see what's going to happen when you distribute. The 30 is going to go to both of the numerators inside of the top numerator. This 30 down here, let me use the identifier. This 30 down here is going to go to both of these numerators. The 1 does not affect these denominators. The 1 does not affect them. Is that clear? Yeah? No? If not, you need to ask instead of sitting, so make sure you ask. What does this become? Without simplifying first. Don't simplify. Just distribute. What does it become? It's not tough. Right.
40x over 6.
Generalize for me, Ryan. It's going to look the same as this, except everything is going to have what?
30.
Yeah. Okay, so take a look. 30x over 6 is now there. 30x over 3 is now there. On the bottom, 30x over 5. Now here it's a little tougher. What is it going to be?
210 over 2.
Yeah. Again, 30 times 7 is 210. So we're going to do that for that part. And what do you notice, guys? What is this? A coincidence? No, I think not. Everything can simplify. How come? Because we found the LCD. The LCD contains factors of the original numbers that had factors originally. The prime factors of 6 were 3 and 2. Well, those are in 30, so that's going to simplify. The factors of 10 are 5 and 2, and those both go into 210 also. So they're all going to simplify. Now it's just a means of simplification. Okay? Simplification. Who's got it for me? Simplify each of these fractions. Tell me what we got. Okay, you want to do this for us?
Sure.
All right.
5x minus 10x over 6x minus 21.
Which reduces to?
I'm going to say 36. 36 is even efficient.
Oh, these are all 30s, remember? It's just me not writing neatly.
Wouldn't the top become negative 5x?
Yeah, good. That's it. Any questions on this one? Good? Okay. You could factor out a 3 of the denominator if you wanted to, right? So we're all clear? Multiple choice question? Number 2. This is no more difficult. It's the same problem. But look at the denominators. They're already factored. The factor of the first denominator is x plus 5. So we have to think to ourselves, a least common denominator is the product of all of the factors. Well, what factors do you see in the denominators here? What's one of the denominators? You look like you're going to say it.
X plus 1.
Yeah, that's one of the factors. This denominator is really what? This is really 1 times x plus 5. This is 1 times x plus 3. This is 1 times x plus 5. So the factors of all the denominators are 1, x plus 5, and x minus 3. So list them. Just multiply them together. There's your LCD. 1 times x plus 5 times x minus 3. It's again the same question as the other day. If I were to find an LCD, what's missing? What's missing? Ian, on the top fraction, what's missing? From between this right here and this denominator, what's missing? What's missing here? And then, what's missing here? Yeah. So you think to yourselves, if you had put those missing parts there, what would each of these denominators look like? They would look like this, right? What you see right here. So this is your LCD. So we've taken step 1 and we're done. The 1 doesn't matter, obviously. Yeah, I just put it there just to show. Next, step 2 says to multiply by that LCD. So this is where it's going to look a little bit messy. So what do we do? Take a look. And this looks complicated, but it's actually not. And in a minute, you're going to see that I'm going to show you a little trick that makes you not have to do this every time. What you see is the following. Here's the original fraction, right here. Here's the LCD. We take the LCD, oh, I made a typo. It's plus. We take the LCD and we multiply it by the LCD over 1 over the LCD over 1. Now, what you're going to notice is that when you multiply this right here with this right here, what's going to cancel? Yeah, see that? The x plus 5's cancel. Because really this has parentheses around it. so does this, so does this, and so does this whole thing. See that? That's what we have to remember, and that's the tough part. So now watch. In the numerator, cancel, cancel. This numerator becomes 3 times the quantity x minus 3. Isn't that kind of crazy to think about? The x plus 5 is canceled. So here's what I think about. Whatever's missing down here is what's going to remain left over. Again, listen carefully. Whatever is missing here from the LCD is what will remain afterward. The x minus 3 is missing down here. So when you put this LCD, these are going to cancel, leaving behind the x minus 3 in the numerator. So whatever's missing in the denominator is left behind in the numerator. It will always work that way. Is that clear? Say it back to me again. What did I just say? Somebody say it. Ryan.
Whenever you multiply in the numerator, whatever you cancel out, whatever is left in the numerator.
Yeah, so whatever was missing in the denominator of that fraction, write this down. Whatever is missing in the denominator of one individual fraction is what will be left over after simplification of that fraction. Okay, always, 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 always. It really helps. So again, whatever's missing in the denominator of an individual fraction is what will be left over when that fraction gets simplified. If you need water, feel free. I'm just saying. So, in the bottom now, this is when it gets tough. Because we need to distribute this LCD down here that you see to both of these fractions. And I would like you to do it in your head, because it just gets messy to write. You see what I'm saying? So look, what's missing in this denominator right here? This is not a tough question. What's missing, Julia? X plus 5. So what's going to be left over in the numerator in this one when we multiply through? X plus 5 is going to be the thing that is left over in the numerator because the x minus 3 cancels. Second part here. What's missing in this denominator?
X minus 3.
Yeah, so the x plus 5 will cancel here, right? So what's going to be left over? X minus 3. So here's what I think about it. I'll do it color-coded. When I distribute this to this one here, these cancel, right? Everybody see that? So we're left with, for that part, 2 times x plus 5. Remember the 2 in the numerator that exists here still. Now, at that point in time, I can go back, oops, didn't mean to do that, and think to myself, now when I distribute, remember this is still here now, the x minus 3 is no longer canceled. When I distribute it here, the x plus 5 cancels, leaving behind the x minus 3 that's still there. And there's a 1 in front. So we have plus 1 times x minus 3. Okay? And that's what your answer is once simplified. Let's go ahead and simplify what that looks like. But this process is not difficult. It's just about remembering what to do. Okay? And thinking logically and visually about what's going on. Now, I could leave the numerator alone for a minute because it's factored and simplify the denominator first, just because there might be a simplification possible. Does everybody see that? The numerator is factored, leave it. The denominator has sums. Sum them together, whatever you can. This is really 2x plus 10, and that 1 means nothing. So we have 3x plus 7. Can you factor anything out of 3x plus 7? So there's nothing to simplify with the numerator. So you could either leave it like this, or you can multiply out the numerator. How we doing, guys? Questions so far? Questions?
Would you split it into 2?
No, because the denominator is a binomial. If the denominator was a monomial, you could break it up. Good? Yeah? Okay. Let's go on to one more. We'll finish with this last one here for today. There's 5 examples total, so we're going to still work on this section. We're not done. Let's take a look at an example of multiple choice. Okay? I thought, hey, you know what? We might as well do a multiple choice, right? No? kidding. You gotta look at your face like, what? Alright, so let's take a look at an example with multiple choice. So for this problem, we've got a, 5-time complex fraction, looks like. There are 5 parts to it. And you don't even notice it, but the ones are fractions. What are they? They're 1 over 1. So those ones are fractions, okay? Now, look at all of your denominators. What are the factors in all of the denominators? I'm going to point, and you tell me what the factors of the denominator are. Okay? Ready? Factors of this denominator. 1. Factors of this. What is the factors of this? X and X, or 1x and x. Right? Are there x and another x there? Factors of this denominator. This one. X and 1. So all I heard was x, 1, and 1, right? Those were all the denominators, and those are the most of them. So that means that my LCD of this problem is going to be what? X squared. Remember, this denominator, here's one of my denominators, the factor. The first denominator, second denominator, third denominator, fourth denominator, fifth denominator. Think about it. The only factors are 1 and x. But look at the denominator, the third one down. Doesn't it repeat x twice? So that means that it must have at least that many x's at all times. If we had done a prime factorization where you had like a number like 4 in the denominator, what does that factor into? What does 4 factor into? 2 and 2. So you would have to use 2 twice because 2 shows up twice in one of the factors. Okay? So if any of the factors are repeated, it needs to be repeated that many times in the LCD. Again, write this down. If a factor is repeated in one of those denominators, not in 2 of them, but in 1 alone, then it needs to be repeated that many times in the LCD. If a factor is repeated in one of the denominators, then it needs to be repeated that many times in the LCD. So if the LCD is x squared, let's go ahead and go through this process. I'm going to write it, but you're going to do it in your head. You don't have to put the x squared over 1. I've been doing that with the LCD because it's clear now that the 1 gets distributed to all the denominators, but you don't have to if you don't want to. Is that clear? There's your 5 choices. Let's take a look at this problem. Distributing an x squared to each of these, right? Distribute, 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 distribute. Somebody help me out with the numerator. What does that become? The major numerator. Chris.
X squared plus 3x plus, wouldn't it just be 2?
Good. Very good, Chris. So he's doing his cancellations. X squared does not cancel with anything with 1. But x squared cancels with one of the x's and 3 over x, leaving behind just a 3 and an x up top. But 2 over x squared, the x squared is just canceled, leaving behind the 2 only. Good job, Chris. Next part. We're going to look at it and see if it's factorable. Denominator. Who's got the denominator? Ian. Well done, Ian. Plus 2. There you go, good. Because remember, there's only one x down here, so this cancels with just one of those x's, leaving behind an x on there. Okay? I hate when that happens. Really? Yeah, I don't know why it does that a lot. No. Yeah, I know. It's not there. I thought that was the bottom line. Now, Ryan, you made a good point. Let's go ahead and factor. This answer does not show up. Does everybody see that? This answer does not show up in the choices. Take a look at the choices, please. None of those are right. C is the closest, right? C is the closest, but it's not right. Where might C come from? Where might C come from? Somebody adding like a 1 and 2 together here, right? You're getting the 3? Or trying to think of another way. No, I don't see another way of that coming up as a choice. Sure. X plus 2, x plus 1. All over?
Over, if you factor out x, you just x plus 2.
Canceling?
X plus 2.
Leaving behind?
1, x plus 1 over x.
Which is choice?
B.
Yep. If people canceled those x's, what would be left? Yeah, some people might choose 1. If people cancel the x's and put a 1 left behind, if they cancel these two x's here, okay, and leave a 1 here and a 1 here, they get 1 plus 1 over 1. So it's 2 over 1. That's this choice right here. If you cancel these x's and ignore them and leave them with just pretty much cover them up altogether, you're left with this 1. That's why that's there. Okay, do you see how they're like the common mistakes? All right. Any questions on this problem? We're going to stop there for today. We're going to pick up with this next class. Okay? So when are we going to pick up with this on? So what we're going to do now is we're going to take a look at an example where the exponents are negative, which is going to indicate to me right away that we're going to have some sort of a fraction involved in the problem. Okay, so which is going to give us the fact that we're using complex fractions. So can somebody remember or think back and tell me, what do you do when you see a negative exponent? How do you write it instead? Joe?
Oh, no, you put it on the bottom.
Yeah, good. So how does it work in this kind of a problem though?
Maybe R1 plus S1 or R3 plus S2.
Doesn't work that way. It's a good idea though, Joe. You're saying switch the entire fraction, but the sums there. The sums indicate that we can't just start switching stuff. We have to do them individually, as if they're each individual fractions, all 4 of them.
So 1 over R.
Yeah, go ahead, try again.
1 over R to the third plus 1 over S to the third over 1 over R plus 1 over S.
Good. Very good, Joe. But I agree with you. It's tempting to just flip the whole fraction because the negative and positive, but that would be if they were all factors. If they were all multiplying, so if this was a multiplication sign instead of an addition sign, you could just simply invert the entire fraction. So this is where we're at now. And now you can see that we have complex fractions, the examples we've been working with, because we have fractions within fractions. So we need to look at the entire problem and look at all 4 of the fractions and say to ourselves, what is the common denominator of all 4 of these fractions in this problem? What would the common denominator be? And this is a little bit tough to see right away. So we've got r cubed, we've got s cubed, we've got r, and we've got s as the 4 fractions.
How did I do R cubed and S cubed?
Yeah, why?
Because they're all going. Because it's going down there.
Tough question to answer, isn't it?
Because it's R times R times R times S times S. It's just R cubed is R.
Good.
And S is S.
Good. And then r and s are already what?
It's like, they go into
Yeah, they're already contained in them. So take a look, and this is how you always check. Look at your LCD, R, 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 S, S, S. Does every denominator appear in here somewhere? Yes, it does. The denominator R cubed clearly appears in these 3 R's. The denominator S cubed appears right here. The denominator R appears right there in the front. There's the R. The denominator S appears right there, the first S. So as long as they appear in all of them, it is the LCD. Okay? So now what do we do? What's the method that we use to simplify these?
multiply by R cubed, S cubed, and 1.
Yeah, so let's do that. R cubed S cubed over 1. R cubed S cubed over 1. And we remember to put parentheses around the entire thing. Okay, again, always multiply the top and the bottom by that LCD. And I'm going to extend my fraction line. And what do we get? What do we get as a result of this? Yeah, so what we're going to do, we're going to distribute, right? We're going to remember to distribute first, like that, and like that, and like that, and like that. And you know what? If you get confused as to what should be on the next line, since all the numerators are 1s, just simply put R cubed, S cubed in all of the numerators. Because that's what it would turn out to look like, right? R cubed, S cubed, this numerator, this term here, would end up here, and it would also end up here when you distribute. It would also end up here and here when you distribute. as a result. So you can just simply in your mind put r cubed s cubed in all of the numerators and then simplify. Kate, what do you get when you simplify that? When you put r cubed s cubed in all of those numerators?
You get 2r cubed, 2s cubed, or would it just be like 2r cubed s cubed?
Well, let's see here. Let's look at the first one, Kate. R cubed s cubed, right? Because that's what you get when you multiply. What cancels?
The r cubes, oh, okay.
So what are you left with?
S cubed.
Okay. Over here, put r cubed s cubed in the numerator because that's what it would look like.
And then it's going to cancel the s cubed, so it's going to be r s cubed plus r cubed.
Yeah. Denominator. Keep going, Kate.
Okay, and the next one, we're going to put r cubed, s cubed. One of the r's is going to cancel, and it's going to cancel the bottom one, so it's going to be r squared s cubed.
Yes, very good.
And then it's going to be r cubed s squared.
Very good. Which is a bit confusing, right? It's tough to keep track of. It's like, what is it? You say those things that are in English, they're tongue twisters, right? They're alliterative, and it's tough to say them. It's almost tough to do something like this too, because there's a lot of room for error. It's like r cubed, s squared, r cubed, and then you have the numerator canceling. So there's a lot going on here. Now, at this point in time, it is somewhat difficult to see what you should do next. Can anybody take not a guess, but an educated guess, really, as to what we can do next for this problem? Right. Split it up. Can't split it up here. No, you only split it up, remember, right? If the denominator is a monomial.
Couldn't you do S that whole down there in R?
Oh, absolutely. Sorry, if that's what you meant. Yeah, but does that simplify anything? You could do that, technically. Yeah, you could divide the entire denominator into each of the numerators and write them separately, but it will not simplify anything for us. But we can do something. What was the next step? Yeah, the denominator clearly has a GCF. How many S's are in both terms in the denominator? How many S's are there? There's 2 of them. How many R's are there? How many R's are there in the denominator of both terms? Also 2, right? There's 2 R's here and there's 3 here. So we could take at least 2 of them out. There's 3 of them here and 2 of them here. So we could take at least 2 of them out. So let's take out r squared s squared. Julia, does that make sense? You had a look on your face. Okay, just making sure. Chris, you want to tell me what's left over when I take out r squared s squared out of the first term?
Isn't it just s cubed and r cubed?
Close. It's just s and r. Take a look. If I take s squared out of the first term, it's just an s that's left, right? So don't forget to drop off those exponents. Now, if you ever forgot, what do you do if you forget how to factor out the GCF? What's the easy way to always check that you took out the right thing? Yeah, multiply back through, okay, to see if you get the right answer. Or you can divide the original parts by the GCF. Just literally, in your mind, put r squared s squared in both of those spots. And see what the result is. The result of dividing by that term should be this s plus r quantity. Okay? Numerator. Who's got that one for me? What do we got for the numerator? You got to think back.
You go like a 1 cubed or something.
Not a 1 cubed. It's a good idea, though. Doesn't do anything, right? Come on, people. Think back. We did this type of factoring.
Oh, difference of cubes.
Close. It's not a difference, it's a... Yeah, sum. Sum.
Oh, no, I hate it.
Sum of cubes.
It's that equation that you're really going to want to remember.
What?
I feel like everything's something.
Okay. Sum of cubes.
You don't want to remember pre-calc.
Is it 2SR or is it SR? Is there a 2 there? I feel like I put an extra 2 there for some reason.
But isn't it?
Check the formula. You check the formula?
Oh, it's not sure.
Check your notes, people. Was there a 2 in the middle term? For some difference of cubes? There should be.
Yeah, it was 2a minus 2ab.
Yeah. Because in my notes I only have a 1 written down, and I'm just looking at my notes now. I gotta correct that.
She can always watch her class.
I only have SR there.
She's so interested in
No, it's just really weird. Like there's a direct view. Like the windows
Well,
look
we're, I mean,
directly
what
into
did you
each other.
expect? Did you expect like a valley and a couple mountains?
Joe, too much sarcasm, Joe. Now, what happens here? As a result of this, what cancels? Yeah, S plus R cancels. We got factors now. Cancel them. And we're left with our final answer there. Okay, we're left with our final answer there. Any questions on this one? Jerry,
It's not necessary for us to factor it once we.
can you factor that numerator?
It's not.
It's impossible.
Oh.
Remember? It's always impossible to factor the numerator with some difference of q's. It is already in its most factored form.
That's just one.
Thank you, Hannah. No 2 there. Scratch the 2. For some crazy reason, I was imagining that there was a 2 there.
Because usually your most times something's usually.
Yeah, you know what it is? The 2 comes from the quantity a plus b quantity squared. You get a 2 in the middle term. It's a squared plus 2ab plus b squared. Okay. See, even I don't have that memorized. I have to do that. All right, let's take a look at the last example here. So this one says express f of x as a single fraction. So f of x. And this seems to throw people for a little bit of a loop here, a little bit confusing at first, simply because when you take a look at this, you're taking f of x and you're plugging it into itself. Right? Isn't that what it says? F of x. So let's reiterate and go back, just to recall in our memory. What would f of 2 look like for this kind of a problem? What would you do for f of 2? Right.
X is 2.
Yeah, so what would it look like? Tell me.
X, 2 over 3, or 2 over 2 is 1.
Yeah, which is 2 over 3. Very good. Everybody agrees with that? If it was f of 2, you take the 2, and since the 2 replaces the x right here, it goes in for x there, and it goes in for x there. Okay. Agreed? But now, 2 is not replacing x. F of x is replacing x. So what would this one look like if we have to take f of x and plug it into itself? Julia.
It's going to be x over x plus 1 over x plus 1.
Yeah, very good. Okay. So what are we doing in this problem? We're taking the original function and we're plugging it into itself wherever x is located. Okay, just like f of g of x, you would take the function g of x and plug it in up here, and you would plug it in over here. Right? If it was f of g of x, you would plug it in these 2 spots. In the same case here, we take f of x and plug it into itself. And now it's clearly a complex fraction. What do we do next? Okay. Yeah. This one is a little bit obvious yet tricky because people get confused. There's really a 1 in this denominator, remember? So the LCD is just x plus 1. Okay? Think about it. The 1, it's in there, it's in the front. There's a front 1 in front of the entire quantity. X plus 1 is in both those denominators. So let's multiply by x plus 1, okay, over x plus 1. See what I have to do there, by the way? I have to put that major parentheses around the original full denominator to remember to distribute the x plus 1 to every term. What happens in the numerator? And this is quite convenient. What happens in the numerator? Yeah, it just becomes x. Notice, cancel, cancel. Leaving behind x only. But the denominator we have to remember to distribute. So please don't just cancel the x plus 1s right away because you're going to forget about that 1 there. So when you're distributing, the first time when you multiply through over here, yeah, the x plus 1s, they're definitely going to cancel. Right? You're going to get the x plus 1 over x plus 1 leaving behind just the x in that denominator. Again, this is going to cancel with this. Okay, these are going to cancel each other when distributed, leaving behind just the x. But what's left behind over here? What's left behind over here? Kate? Yeah, x plus 1. Because this x plus 1 needs to get distributed here also, and there's nothing to cancel with it. So you're left behind with another x plus 1, yielding a final answer of x over 2x plus 1. Okay?
These look so intimidating.
They do. They definitely do. I agree with you, Joe, because they're really complex at first. Right? But once you simplify them a little bit, they're not terrible. They're not terrible. Okay? I'm trying to keep them on the screen. Yeah, no. What we're gonna do next is we're gonna take a look at equations that have rational expressions. So, like, imagine an equation with all the fractions involved and how to get rid of them. But it's the same technique. Find the LCD, multiply the whole equation by the LCD. Like, it's the same process over and over again. This is going to lead us into graphing rational functions. So, again, this is our final answer. We cannot really simplify this at all. It's impossible. Don't cancel the x's. Those are add-ins in the denominator. Okay, it's common, some people want to cancel these x's and leave behind 1 over 2 plus 1. You cannot cancel the x's. Any questions on this one? Want to do one more? Let's do one more. How about something like this? Try this on your own. See how you can do. Try this one on your own. Come up with your LCD, multiply through, and simplify. What's our LCD? Yeah, x squared minus 1. Good, Ryan. And how do you know that? I'm sorry? Okay, but I need more than that, Ryan. It's not obvious to everybody, so make it obvious. What could you do to make it obvious?
Divided the line of all denominators, and I saw x was they all go into x squared. All the x's go into x squared.
It's not how you do it, Ryan. You got to look at factors. Remember factors. What does the denominator of the denominator factor into?
X squared. We're gonna factor it.
Yeah.
X squared. Really, difference of squares.
Yeah, so what does it factor into? Tell me what the factors
X
are.
squared plus 1x. I mean x plus 1x minus 1.
Yeah, there you go. Now it's obvious. That's what I'm getting at, okay? Once you do this, it's clear to see that the LCD is just x plus 1, x minus 1, which is really x squared minus 1, but it's because, look at all of your denominators now. Now they are common. You can see that they're, like the x plus 1 shows up in the other one, okay? So the LCD, you're correct, is x plus 1, x minus 1. And let's list our LCD in factored form, so that when we distribute it, we can clearly see the parts of it that do cancel. Does this make sense? If you put x squared minus 1 as your LCD, it might not be obvious what cancels when you distribute. But now it's quite obvious. So let's go ahead and distribute that to each of these terms. So what's what I'm going to do? X plus 1, x minus 1, all over x plus 1, x minus 1. Okay, distributing here and distributing here. This one just goes right here. So, Jared, go. What do you got?
X minus 1, and then you write your x minus 1 minus 4x minus 4.
Good. 4x plus. Oh, you distributed already?
Yeah.
Okay.
Plus and negative.
Not a problem. Okay. Continue.
So all over 7x.
Yeah, very good, Jared. So again, let's take a look at this. We've got cancel, cancel. leaving behind 7x in the bottom. That's the easy part. The numerator, though, we have to remember to distribute. So here, this x plus 1 cancels this x plus 1, leaving behind x minus 1 up here. That's where this comes from, right here. Then we go back, and we see that this x minus 1 cancels this x minus 1, leaving behind an x plus 1 up here. Okay, and that's where this comes from, right here. And then Jared just distributed everything out. And what does it turn out to be as a final simplified answer?
Negative 3x
Negative 3x,
plus 3. Plus 3.
be careful,
Minus.
minus 5.
Or plus 4.
Ah, there you go. You know what it is? It's this negative 4 here, Julia. Distributing the negative 4. Make sure that's a negative 4. Okay? So negative 3x minus 5 all over 7x. Joe, can I simplify this? Probably not. Probably not. I could do this if I wanted to, though. Yeah, you could separate it.
But I mean, not even doing much.
I mean, the x's cancel, right? And the 3x and the 7x, that part? That's about it. But is that really more simplified than the last answer? Not really. It's no different.
You said both ways, right?
Yeah. Absolutely. Okay? So either answer is completely fine in this problem. Any questions on this? So what's the goal? What's the goal? What are we trying to do? What's the word? Yeah, simplify. That's the goal. Simplification. And by what means? We find a what? Louder? LCD. Good, Chris. And then Kate, what do we do with that LCD?
We multiply
Yeah. Multiply what?
the numerator,
And the?
denominator.
Good. Because we cannot multiply by just one, right? Remember, with a rational expression, if you're going to multiply by something, it's got to be over that number. So for example, if you multiply by 5, it's got to be 5 over 5, always. Okay? Or else you're changing the value of the expression. So that's why we multiplied here by x plus 1, x minus 1 over x plus 1, x minus 1. Your homework, take a look. It's 3 through 24 multiples of 3. The mixed review shouldn't be tough. Okay, that's one of the few ones I've given you this year. I don't give you many of the mixed reviews, but I'm going to try to do a little more of it just from the rest of the year simply because you have finals coming up. So we'll help you for your
Are you gonna do like an all-inclusive one?
absolutely. Cumulative meaning? Yeah.
Is it like on my
All maths are always going to be that way, guys, for the rest of your